the problem in the entire domain, then I need to be a little more careful, because u double dash is 0 everywhere but at the interface. At the interface, it's actually singular because u undergoes a jump. So u dash, or the velocity gradient, is a delta function, and u double dash is a derivative of a delta function. This is if you were to solve the entire domain at one go. But if you don't want to do that, you want to do it at individual layer and then try to apply the matching of kinematic and dynamic boundary condition, then in individual layers, u is a uniform quantity. So u double dash is equal to 0. So what kind of boundary condition should we apply? So the first boundary condition is the boundary condition called as the kinematic boundary condition. So the kinematic boundary condition says that the material or the interface, which is Z. So now if I say that the interface has been curled up and Z is equal to eta of x comma t, then ddt of Z minus eta is equal to 0. I mean, this is actually eta of x comma t, right? That Z minus eta is the equation of that interface between the two liquids, and it is a material surface. So by definition of a material surface, it should actually move and there should be no transport across that interface. So which means that ddt, the material derivative of Z minus eta, should be 0. So now if I write this out, ddt of Z is going to be the vertical velocity, which is uz, is equal to d eta dt. So at the interface, the vertical velocity is equal to the material derivative of the interface equation, eta. Now if I write this out, dou eta dou t plus u, in this case, so this is the material derivative evaluated at the interface. So this would be ux dou eta dou x. All of this are to be evaluated at the perturbed interface. So this is
of about 8.
Let me do this once more. ddt minus z of is equal to 0. So dz dt is going to be uz, which will then be equal to d eta dt, which will then be dou eta dou t. If you have a pen and paper, you can also work this along. I mean, these are reasonably simple algebra, but it actually helps you get a feel for it. Just doing the dirty work makes you actually aware how these calculations are done. Now, we are operating in the regime of linear stability analysis, right? So if I'm operating in the regime of linear stability analysis, then I need to linearize all of these terms. So sorry for that thing popping off every now and then. So I have uz as dou eta dou t plus ux dou eta dou x is equal to dou eta dou t. So now if I say that this particular quantity, so this is the interface is basically something that's whether you approach from the top or you approach from the bottom, it doesn't really undergo a change. So if I apply this condition, then I would have dou eta dou t in the top layer. So this is the top layer, dou eta dou t, u bar dou eta dou x is equal to uz, and bottom layer dou eta dou t plus, there is no u bar there, so it will be the perturbation ux dou eta dou x, and that I'm going to cancel because of nonlinearity. So there would be no contribution whatsoever from this advection term. Similarly, in the top layer also, there would be a term which would be ux dou eta dou x, and that's again something I'm going to ignore. So what do we have here? So whether the vertical velocity of a fluid parcel as it comes from the top and the bottom should be equal. So there is no background vertical velocity. There is only the perturbation vertical velocity. So the perturbation vertical velocity should be continuous. The continuity of the perturbation vertical velocity would tell us that when evaluated from uz, so if I now, let me write this properly. So in the top layer, uz okay. So now let me not skip steps. I'll just assume a normal mode form. So if I assume a normal mode form of e to the power ikx x minus omega t, then I can write this as minus I omega eta plus ikx u eta is equal to uz. And just to make a distinction, I'll put a plus here to say that the vertical velocity uz evaluated in the top layer is uz plus, and then the bottom layer is going to be minus I omega is equal to uz minus. So from both the layers, I'm going to get uz plus is equal to minus omega minus kux u bar. And from the bottom layer, it should be minus I omega. And these two should be equal because the interface, whether you see it from the top or you see it from the bottom, it should not matter. They should be identical to each other. Right? So now if I go and try to actually apply the kinematic boundary condition. So if I say that, okay, fine, this is my, so I evaluate my uz, I solve my Rayleigh equation. So the Rayleigh equation is d square dz square minus kx square. So that would have solution in the form of exponential of minus kxz. And the bottom one would have a solution in the form of exponential kxz. So there would be two solutions to this equation. There would be an exponential minus kxz and there would be an exponential plus kxz. And when I'm in the top layer, I would assume a decaying exponential, and in the bottom layer, I would basically assume a growing exponential, but finally the solution will go to zero because z is actually negative in the bottom layer and z is positive in the top layer. So if I assume these two forms of the solution, so this is my uz top and this is my uz bottom. And I know that I should have eta evaluated either from the top or the bottom should be equal to each other. There should be no discrepancy whatsoever. Then that would actually give me okay. So I think let me do one thing. I'll just getting a bit. Okay, so I'll just work out the algebra here and then go back. I was trying to do it there, but it's just too many interruptions there. So I have the top layer, which is moving with velocity u, and the bottom layer is at rest. This is my z-axis. This is my x-axis. Now, this is my Rayleigh equation. And since u in each layer, if I solve it individually in each layer, u is uniform. So that u double dash term goes to 0. So top layer, it's which gives us uz is equal to some constant a1 exponential of minus kxz plus a1 star exponential of plus kxz. Similarly, for the bottom layer, it is d square dz square minus kx square. It's the same equation, nothing changes, even though the bottom layer is static and the top layer is in motion. In terms of the stability equation, nothing changes. So you get the same equation. Now we want uz to go to 0 as z goes to plus or minus infinity, which means I can completely ignore this term a1 star in the top layer and a2 star in the bottom layer. So now what about the kinematic boundary condition? So I need boundary conditions. So what are the unknowns in my problem? My unknowns in my problem, they are a1, a2, and obviously the eigenvalue omega that's there in the problem. See, the omega is not there in the equation. So we would expect omega to somehow come from my boundary condition. So if I write my uz's equation is dou eta dou t plus ux dou eta dou x. So uz in the top layer is dou eta dou t plus u bar dou eta dou x plus ux perturbation. I'm not making the distinction. So this ux is the perturbation, and this term I'm going to drop because that's a term which is nonlinear. Similarly, uz bottom will be dou eta dou t plus ux dou eta dou x, which is again going to be dropped. Now, if I write them in their normal mode form, this would be minus I omega eta plus ikx u bar eta. So uz top is going to be minus I eta omega minus kx u bar. And similarly, uz bottom is going to be minus I omega eta. Now, what do we have? Eta, whether you find from the top or the bottom, should be the same, which means eta from the top should be uz top minus I omega minus kx u bar, and eta from the bottom should be uz bottom by minus I omega. And they should be equal to each other, which means I have a boundary condition which is omega times uz top is equal to omega minus kx u bar uz bottom. So if the interface was not perturbed, then the vertical velocity across that perturbed location should be continuous. There should not be any jump in the vertical velocity. But because you have now perturbed the interface, the uniform flow, which is moving in the x direction, that uniform flow in the x direction acting on a curved interface is going to give rise to some kind of a normal component on the vertical interface. And that can only be compensated if you create a uz. So you need a compensatory uz that a jump in uz that is required to actually compensate for the fact that the imposed flow evaluated on a perturbed location would give rise to some normal velocity at that perturbed location. So that's why you have this. If u bar was 0, then you would have the uz on the both location should be continuous, but that's not. Okay, so now we have expressions for uz, and let's just substitute. So uz is a exponential minus kxz. So I'll have omega a exponential minus kxz evaluated at z equals 0, because I'm doing linearization. It should actually be z equals eta, but then if I'm doing this in the linear theory, this would be evaluated at z equals 0. And then this will be omega minus kx u bar, and this will be a2 exponential of plus kxz evaluated at z equals 0. So when I do that, I get a1 omega is equal to a2 omega minus kx u bar. Okay. So that's my kinematic boundary condition. So what I can do is I can assume a form of AM1 and A2. So I can choose one of, this is a linear problem. So I can choose one of them, a particular value for one of them, and then I can decide the other one based on the condition. So what I'll do is I'll say A1 is omega minus kx u bar, and just for the convenience of what comes later, I'll multiply it with ikx pi by kx. So you're free to choose one constant because of the linearity of the problem. And A2 automatically then becomes minus ix k inverse omega. Okay, so this is my kinematic boundary condition. Now, what about, so I found out the constants, but I still have an unknown, which is omega. Omega is still an unknown in my problem. So how do I basically go about and find omega in my problem? So to find omega in my problem, I need to actually do a dynamic boundary condition. So the dynamic boundary condition, if you write it in terms of the total stress, so that would be sigma dot n. That's the stress that is, I mean, the normal component of the stress that is acting. And this, when evaluated at z equals zeta, the jump in this quantity should be equal to the surface tension times divergence of n. So n here is the unit normal. So we have, let me see if I can pull out. So n would be gradient of eta minus z, because that's the equation of the interface divided by gradient of eta minus z, because you want it to be a unit normal. So this tells you this is a normal to the interface, and then you divide this by the magnitude, which gives you a unit normal. Now, we are doing an inviscid problem. We don't have any effects of viscosity included into our calculation. So since this is entirely inviscid, what we are going to do here is the contribution from the stress is only going to come from pressure. So we will have a jump in pressure. So P total at Z equals 0 plus minus P total at Z equals 0 minus is equal to gamma divergence of n. So actually, let me write it without the linearization first. Z equals eta plus, and this is on the other side at eta minus. Now, what is the total pressure? The total pressure would be the hydrostatic contribution, which is P naught minus rho gz plus a perturbation, P of x comma z comma t. So if I evaluate the total pressure difference across the interface and then apply linearization. So this would be P naught minus, so the top layer has density rho 1 g eta plus the perturbation at z equals 0 plus, because the perturbation evaluated at z equals eta would be irrelevant. That's a nonlinear term. So I write the perturbation at z equals 0 plus. Similarly, the total pressure at the lower side of the interface would be P naught minus rho 2 g eta. That's the hydrostatic pressure. So you have the interface. This is rho 1, this is rho 2. So the total pressure at any location here would be the atmospheric pressure plus the hydrostatic so this is hydrostatic contribution, which is rho gz. So this is rho 1 gz, so z equals to eta, and from the bottom side it is rho 2 gz. Just interrupt me if you are not following some of these parts. So I'm just taking it step by step without making any approximation. If something still seems unclear, just ask me to pause. So then I have the perturbation pressure at z equals 0 minus. So this is the pressure in the bottom region, and this is the pressure in the top region. Okay, so I think I have used, so let me write for total, because I'm using top for T, so this is tot. So this then becomes ρ2 minus ρ1 g eta, and this is the pressure in the top region, this is the pressure in the bottom region. So then I have pressure in the bottom minus pressure in the top. This is evaluated at z equals 0 plus. Now how do I find pressure? So to find pressure, I could either use Bernoulli's equation, because the fluid that is there in either of the layers, they are irrotational. I have a uniform flow in the top layer and a zero flow in the bottom layer. So it's an irrotational flow there. And if I assume irrotational disturbances, I can use Bernoulli's. Or I could also go back to my momentum equation, my x momentum equation, and I can write it out. So that is rho dou ux dou t plus u bar dou ux dou x plus uz dou u bar. So this is the x momentum equation under the linear theory, minus dou p dou x. So if for our problem, in either layer, the shear is 0, and the top layer has a u bar, the bottom layer does not have a u bar. So what I can do is, I can write this as rho dou ux dou t plus u bar dou ux dou x equals minus dou p dou x. Now, if I write it at in the individual layer, so in individual layer, I can write the pressure as rho dou u, it's u minus c, if I assume the Fourier mode, d psi dz. So d psi dz would be the stream function. So I'll just write it back maybe. So it's rho u minus c ux. So this is my expression for pressure. So if I now go back into my previous equation, the jump in the total pressure. So I had P tot Z equals eta minus, this would be rho 2 minus rho 1 g eta so this minus the top layer has rho 1 u bar minus c ux top at z equals 0 plus, and the bottom layer would be rho 2 u is 0 ux bottom at z equals 0 plus. So this is rho 2 minus rho 1 g eta plus rho 2. So it's minus rho 2 c ux bottom z equals 0 plus minus rho 1 u bar minus c ux top z equals 0 plus. And how do I find ux? So ikx ux plus duz is equal to 0. So that tells me what is ux, I by kx duz. How do I find eta? We have already done so before. What is the expression of eta in terms of uz? So if you do all of that, you would be able to substitute for ux and eta in both the expression. Now, how about the unit normal? So the unit normal is gradient of eta minus z modulus of gradient of eta minus z. So, and I need to basically take a divergence of that. So this in the linear limit would be dou eta dou x along the x direction minus a unit vector in the negative z direction. So this is a unit normal pointing from the top fluid to the bottom fluid. So if there was no perturbation, if the interface was flat, it would just be the unit vector in the z direction. Because of the interface actually not being flat, there is a correction that comes in. This is obviously a linear approximation. In the nonlinear limit, there would be other terms involving the curvature, because this is actually the curvature. So divergence of n cap, that would be in the linear limit, dou eta dou x square. So if I write divergence of n cap in the normal mode form, that would be minus kx square eta. So if I put all of this together, I'll have a dynamic boundary condition, and this will allow me to solve for omega. So with the kinematic boundary condition, we are able to arrive relation involving the constants. And then with applying the dynamic boundary condition, where you say that the jump in pressure is accounted by surface tension. So the two fluids are, if you say that they're made up of different fluids, they're not the same, then the interface is constituted of a fluid particle from, let's say, the bottom fluid, which is surrounded by, on top, by fluid particle from the top fluid. So as I said, fluid elements inherently will have a cohesive force between them. So if I have a fluid element which is somewhere here in the center, this fluid element is actually being attracted from all directions by like fluid molecules. But a fluid molecule which is sitting at the interface is being attracted by its neighbors from the bottom, and it is attracted, it experiences a differential force from the neighbors who are from the top fluid. And this leads to surface tension. So now, because of surface tension, you are allowed to actually have a jump in the normal stress. And in this case, the normal stress is precisely pressure. So which then gives us our dispersion relation. So the dispersion relation involves the speed with which the top fluid is moving. It has the density of both the layers. It obviously has the wave number. So there is a term which is of gravitational origin. There is a term that is of surface tension origin. And then you have the frequency terms on the right-hand side. So now what we will do, we will look at this in certain limits. So the simplest limit first you can think of is reminiscent of the Kelvin-Helmholtz problems we saw, where you assume that the top and the bottom fluid are identical. And hence, there is no surface tension. So gamma is equal to 0, ρ2 is equal to ρ1. If you do that substitution, then you are going to have these as the non-zero terms. Ρ2 is equal to ρ1. So when you solve that quadratic equation, you find that omega by kxu is equal to 1 plus or minus I by 2. Now this immediately has two features. One, that the growth rate is found because there's an imaginary part of omega which is non-zero, and the imaginary part of omega being non-zero tells you that the mode is actually going to grow in time. So this is your first signature of an instability, which you can work out when you have two streams flowing past each other. Now, the speed with which it moves is half, and that's because the top layer is moving with velocity u, the bottom layer is at rest. So the unstable mode is actually going to propagate with a speed that is the average of the two layers. So if you had a scenario where the other layer was moving with velocity minus u, then the real part of omega would be 0. So the real part of omega denotes the average speed of the two layers. So in this case, the average speed is u by 2, which is why you get the half there. Now, what about when u is equal to 0? So when u is equal to 0, the top fluid is at rest, bottom fluid is anyway to begin with at rest, but there is a density contrast, and then there is an effect of surface tension. So if we look at this expression, there are two terms, and you could make this still become unstable if rho 2 was smaller than rho 1. So if the bottom fluid was lighter than the top fluid, then this would have been a scenario where omega would have an imaginary part. And this would be, so when rho 2 is less than rho 1, this gives you Rayleigh-Taylor instability. If you remember from the first lecture, we had a video of Rayleigh-Taylor instability. So I said that if you have a layer of water which was lying on top of a layer of air, we know that that is inherently always unstable. That interface which is separating water from air, you cannot sustain that. So here what you are finding out is that there is a possibility you could stabilize it if you have surface tension. And you can work it out that how high should be the surface tension. Or you can ask the other question that how high should be the value of kx such that this term dominates over this term. So we can try to just calculate this. So we can say that if rho 2, so if you have water, so I'll consider a setting water over air. So rho 2 is 1000, rho 1 is 1. So I want to find out at what value of kx. See, if you look at this term, this is a term which is always positive. This term can be made negative if the bottom fluid is lighter than the top fluid. Now, if kx becomes extremely large, then it can dominate over this term. So we can ask the question that how large a kx can I have for a water-air system? So if I look at the term here, rho 2 minus rho 1 by rho 2 plus rho 1, that's almost equal to minus 1. So rho 2 is, so I have, sorry, the top is 1 and bottom is 2. So the numerator is minus 999, the denominator is 1001. So I'll assume that to be roughly equal to 1. If I take G as 10, so then that is 1 into 10 into kx, sorry, minus 1 into 10 into kx, that's the first term. Surface tension is 70 millinewton per meter. So that is 70 into 10 to the power minus 3 into kx cube. And the denominator, so I'll need someone's help with a calculation here. The denominator would be rho 2 plus rho 1, which I'll again take it to be 10 to the power 3. So what would be the value of kx at which this would become stable? What is the critical kx? So this is 10 into 10 to the power 6 divided by 70. If I try to balance it, then I get a kx which is 10 to the power 3 by root 7. If I approximate root 7 as 2.5, then this would be 10 by 4 into 10 cube. That would be 400 meter inverse. Can someone just quickly verify if the answer is around 400 meter inverse?
It's around 380.
Okay. So I need the inverse of that. So the length scale is 2 pi by kx. So 2 pi is roughly 6. So 6 by 4 into 10 to the power minus 2. So that's around 1.5 10 to the power minus 2. So you would have surface tension. So what do we get as an answer? Is that okay?
Yeah.
So what you find here is that if there are waves which are smaller than 2 centimeters, roughly 1 centimeter waves if you have or smaller, then surface tension is actually going to prevent a water air kind of a system from being unstable. So it's going to be really hard for you to actually. So then the other physics which we have not included here is that when you go to smaller and smaller length scales, then viscous effects are also going to actually start playing a role. So you would have the viscous corrections coming into the picture, but you can understand how the two competitions are. So there would be an instability in the problem if you have rho 2, the bottom layer, be lighter than the top layer. So now we will just go back to the case where the bottom layer is heavier than the top layer. So I'll just so we have omega is equal to rho 2 minus rho 1 by rho 2 plus rho 1 gkx plus surface tension term. So for the time being, we will not look into surface tension. So we got omega is equal to gkx rho 2 minus rho 1 by rho 2 plus rho 1. This is omega square. Now, if I assume that, again, it's an air-water system, rho 2 minus rho 1 by rho 2 plus rho 1 is roughly equal to 1. So I can then say that omega square is gkx. So this is the speed of gravity waves. The mode is not unstable. So I have an air-water interface. And if I create some ripple, this is going to propagate and it will have a frequency which will be root g kx. If the wavelength we saw in the previous analysis, if you make this extremely fine scaled, then surface tension is going to become important. So that term which is gamma kx cube, this term will start to become important. But for the time being, we'll ignore that and we'll just think of the gravity wave problem. Now we have done the calculation where the bottom region was, so now imagine there is no flow. The top fluid is air. We are ignoring the dynamics of the top fluid. So we are even throwing that off. We just have water in the bottom region. Now you can either let the bottom region extend all the way to minus infinity, or you can probably put a bottom here. You can say that this is a finite depth pool of water. There is no flow, there is no imposed flow in the system, and you can, for the time being, ignore the dynamics due to surface tension and the dynamics that comes about because of the top air region. So all that taken into account, the frequency would be root gkx. But if you have the bottom region actually being there is a bottom boundary, it's not infinity, then it gets slightly modified. It becomes root gk tan hk, tan hyperbolic kh. So there is an h which appears there. That's the thickness of the pool. Obviously, when the thickness of the pool goes to infinity, tan hyperbolic goes to 1 and you recover what we just had previously. So now the question is, what would the streamline pattern look like in this problem? And more importantly, we'll see something interesting about the path line pattern. So this is slight deviation from what we are saying so far regarding probing the stability of the system. We are now saying that, okay, I have perturbed the system. The system actually have these waves which are propagating. Now we are asking the question that how would fluid particle actually get transported due to these waves? Now this seems like something which is, in a sense, we don't really ask these kinds of questions for classical instability problem. But for the point of view of waves in the ocean, this is a very important question because this gives us some insight regarding the transport that occurs. Now, if I have just a wave which is, let's say, a cos kx, so ux is some a cos kx omega t, and uy was some a prime sine kx minus omega t. If I had a, or u prime or uy or uz, if I had a velocity field of this kind of a traveling wave form, then this, if you ask the question, what would the streamline and path line look like? The path line for this particular case would actually be the fluid particle is going in the forward direction. So the x velocity is an oscillating flow field, and the z velocity is also an oscillating flow field. So imagine you take a toy problem where a fluid parcel moves back and forth in an oscillating manner, cos kx minus omega t, and it also does the vertical oscillation as sine kx minus omega t. So as the wave propagates, this forward and top bottom oscillation, you can solve this as dx dt and dz dt, and you will find that this will actually form a closed orbit. Depending on the value of a and a prime, it will either be a circle or it will be an ellipse, but it will be a closed orbit. This is just a simple propagating wave, and we are asking what kind of a transport occurs. Now for the surface gravity waves that we have worked out, we have obviously just found out the frequency, but while finding the frequency, we'll also be calculating what the velocity field would be. So you had found those were of the form exponential of kz. Now if the depth is actually, if the depth is finite, not infinity, then instead of a single exponential, it will be a combination of exponential, and it will be in terms of cos hyperbolic or sine hyperbolic functions. But for the time being, that detail is just due to the depth, because we will do the analysis by assuming it to be finite depth, and you can let the depth actually go to infinity, and you will get back the same thing that you have done before. So the question is, what kind of a transport would occur due to these waves? So if I now write down the stream function, I have the velocity. So it seems like a straightforward exercise of fluid kinematics that we do in Introduction to Fluid Mechanics, and find out what would be the streamline pattern and what would be the path line pattern. So if I have to find the streamline pattern, this is my ux, this is my vertical velocity. This is what the streamline would look like. So I have the perturbed interface. This is actually a snapshot. This is an instantaneous streamline pattern because the problem is unsteady. And this is how the streamline would look like. Okay. Now, what about path lines? So if you go back, to your equation for the velocity field, you can check that this is dx dt and this is dz dt. You can check that the velocity field that you have, and this is nothing to do with assuming the layer to be finite. You can do this even for infinite depth. All you have to do is replace this with exponential kz. You can do this for any finite or infinite depth. And what you find is that the equation for the path line is a set of coupled equation. So dx dt is exponential kz cos kx minus omega t, and dz dt would be the same thing with a sine kx minus omega t. And for the finite depth in terms of sine hyperbolic and cos hyperbolic. So what this does is, you can't really explicitly solve this. You can solve this numerically, but we won't first do it numerically. We'll first try to say that, let's assume that the displacement it makes from a position is small. So the amplitude of the wave that we are talking about is a small amplitude wave. It's not a very large amplitude wave. So let's make that assumption that it's a small amplitude wave, and how far can we actually go? So you start a particle from the location x0, z0, and then say that they get displaced from this location x0, z0 due to the fluid velocity, ux and w or uz. And you define these Lagrangian coordinates, xi and zeta, which tells you where the particle is located at any instant of time, because these are functions of time. So ux is going to be the time derivative of xi, and uz or w is going to be the time derivative of zeta. So now if I write down the evolution equation, instead of the velocities, if I write it in terms of time derivatives of xi and zeta, and the right hand side, I do a nice thing. Instead of x and z, I substitute for the initial location x0 and z0. Okay, I say instead of z, it's z0, and instead of x, I say x0. So I'm saying that d xi dt is equal to the fluid velocity at a particular location. And the same thing about d xi dt. If I do that, the equation is nearly trivial in terms of solving it, because the entire right-hand side for both the equations are only functions of time. It's not a function of x and z. So I've done a dramatic reduction by writing the right-hand side in both equations explicitly as a function of time with no dependence on the position. So you can integrate this and you will actually find expressions for xi and expressions for zeta, the Lagrangian deviations from its initial location. If you now try to find out what this would look like, so you can take the expression of xi, you can take the expression for zeta, and when you write it out, these would be ellipses that you would actually find, because all of these are just constants. And if you go back to your deep water, so if the depth goes to infinity, that's called the deep water problem. If the depth is kept in the problem, if you say that you are interested in the layer being significantly thin, then you get it in the shallow water limit. So irrespective of that, if you look at the equation for the Lagrangian deviation, so starting from some x0, z0, it would actually be an ellipse. And the radius of the ellipse, or the minor axis, major axis for the ellipse, or the circle in some cases, it would keep shrinking. So they would look like this. As you keep going down, they will look like closed orbits which are shrinking in size. Now, this is an approximation. We started out by saying that we are approximating the velocity field. We are approximating the velocity field by writing it exactly at its initial location. Now, that's not true, because the right-hand side is a function of the instantaneous coordinate. Some question I missed out. Perturbation velocity. Okay, so the question is that the analysis is based on the perturbation velocity field. Does the mean flow matter? So here there is no mean flow at all. We don't have any background flow. We just have a quiescent layer of water, and we are not even taking the dynamics of air into this problem. We are just saying that the boundary condition that is basically being applied is that you have the pressure should actually match to whatever is the atmospheric pressure. You don't even take surface tension into account. So we have stripped the problem into as simple a setting as you can. All of this can be extended with taking the airflow on top, taking surface tension into the picture. All of that can be done. We're just saying that let's keep it as simple as possible, where we have a layer of water. The only complication we're allowing that we can say that the layer of water is of finite depth, and you can later choose to push it to infinity if you want. But the boundary condition, kinematic boundary condition, remains the same. The dynamic boundary condition is that pressure is continuous at the perturbed interface. There is no roll of pressure from the top layer. There is no surface tension effect. So there is no mean flow in this problem also. So this is what you would get as the equation for path lines. There would be ellipses in the problem. Now, that's not the entire story. So we need to actually take into account that the right-hand side which was the fluid velocity field, is not exactly at the location x naught z naught, but we need to go to the next expression. So what we do is we do the next best thing, because we are talking about small amplitudes. The amplitude of the wave is small. So since these are small amplitude, we can do a Taylor series expansion. So we say that the fluid velocity at the location x comma z comma t can be written as the fluid velocity at x naught z naught comma t plus a Taylor series expansion, which is x minus x naught, the fluid velocity gradient in the x direction evaluated at its initial location, z minus z naught, the fluid velocity in the x direction is gradient in the z direction evaluated at x naught z naught. And then there are higher order terms. Now this x minus x naught is nothing but xi, the Lagrangian deviation. And similarly, z minus z naught is again the Lagrangian deviation zeta. And what is xi and what is zeta? So xi is basically the fluid velocity. We just worked it out, right? Xi would be the fluid velocity evaluated at x naught, z naught, comma t prime, integrated all the way from 0 to t. So if you would have started from the initial location and moved with exactly that same velocity in a time interval t, if the amplitude of the wave is small, xi would be that velocity integrated over that window of time. And the same is true for zeta. So this exercise, if I now go ahead and average it over one time period. So I say that let me take the fluid velocity field and I do an averaging over one time period. Now previously we saw when I approximated the right hand side, the fluid velocity field, I said d xi dt is equal to the fluid velocity field at its initial location, and d zeta dt is also the fluid velocity in the z direction and its initial location. I ended up with closed loops. So whether they were ellipse or circle, that depend on what limit you're operating on, but they would be closed loops. So now the question is, if I allow for this correction to come in the problem, so the time average velocity in the previous problem would be 0, because after one time period you come back to the same location. So what would happen now? So I take the velocity field, I've written down it in terms of this Taylor series expansion. Then when I do a time average, the time average of the first term is 0. And then I have the time average of the corrections, which is xi times the gradient at the initial location and zeta times the vertical gradient at the initial location. And you already have these terms present in the problem, right? You have already worked it out because these are to be found at the initial location. So once you do this, you obtain that these would have non-zero time averages. And what does it mean? That the Lagrangian velocity averaged over one time period is non-zero. The Lagrangian velocity in the vertical direction averaged over one time period is 0, but the x component in the direction of the wave propagation after one time period, the Lagrangian velocity field averaged over one time period is not 0, which means after every time period there is going to be a net displacement. So it's not going to be like this. Instead it will, well, it will look like this. So there is going to be a drift in the problem which comes about. So this is trying to make the distinction between finding the Lagrangian velocity. So the Eulerian velocity averaged over one time period would be 0. If you are sitting at a particular location, if you're put your mood in one location and you observe the velocity after one time period, it has to be the same. There is no difference about the velocity. But if you are following a fluid particle, the average Lagrangian velocity is not 0. And it's the difference between the two, the Lagrangian and the Eulerian, which is called as the Stokes drift. In this case, the Eulerian average is 0. So the Stokes drift turns out to be the Lagrangian average, or the average of the Lagrangian velocity. And this is something which is quite crucial, because what you will observe, so you can see some simulations for a bunch of fluid particles which are left on the free surface and some in the interior. And it's very clear for the ones on the free surface that they don't close the loop. They actually make a small drift every time a wave, a crest goes through and a trough comes and again a crest comes in. There is a small drift that actually occurs. So you have found a simple wave in your problem. You have not taken a complicated system. You have just a pool of water, no surface tension, only gravitational restoring mechanism. And what you have obtained here is that there is a possibility of a transport happening in this problem. On the left side, what you see is the comparison of that simple theory that we did by doing a Taylor series expansion, which is the orangish curve, and the blue is what you would get from the numeric. So that's obviously a calculation done by doing the Taylor series expansion. As the amplitude becomes larger, it starts to deviate. But the bigger question is, why does this happen? See, we took a initial example where I said, imagine that you have an oscillation happening in the x direction and an oscillation happening in the vertical direction. And in that case, you can just work it out. You will find that the particle trajectory will just be circular. So why is that in this particular problem, there is a drift? So here, the key feature which leads to the drift is the fact that the velocity field in the vertical direction is an exponentially decaying velocity field. So whether you take the deep water, whether you take this finite depth problem, or you take the deep water limit of an exponential minus kz, the fact is in the vertical direction, normal to the direction of propagation, the fluid velocity, maybe even earlier, see, the fluid velocity, you forget the top layer, you just look at the bottom layer. The fluid velocity is an exponential function of the vertical coordinate, which means as the wave propagates, as the wave is actually going, as a crest goes and a trough comes and another crest comes. And imagine you were being transported by this crest and trough. So you go forward, then you start coming backward. Now, when you are going forward and when you are coming backward, in the top region and the bottom region, the fluid velocity in the x direction is not the same. There is a factor of exponential minus kz. So over this small region that you make, the loop that you make, so when you have gone from the same x location and come back to that same x location, but with a certain vertical displacement, the fluid velocity now that is going back, so it took you forward, you came back, and then the fluid velocity has reversed and it is taking you backward. When it is going in the backward direction, you are at a slightly deeper location. At that deeper location, the background flow is weaker. It is not able to transport you as much as you were able to be transported in the forward direction. Your transport in the forward direction was happening at a location closer to the interface than your transport in the backward direction when you are in a slightly deeper location. So this mismatch in the two transport, where you have a slightly larger transport going forward than a transport going backward, leads you to a drift. If this vertical variation won't be there, you would not find any drift. There would be absolutely no drift in the problem. You would make a perfect orbit and keep making this orbit. So this small change can actually lead to a significant amount of transport that would occur. And this is a visualization done in experiments, because Stokes drift are usually very hard to measure in a lab setting, because you'll constantly have some current that would be created. So you are trying to precisely measure the drift that is occurring over and above if there are any other current in the system. If there is some ambient current, if there is some ambient source, you just want to avoid that actually to find this drift. So it's very hard to find. But you can realize now that the waves that you have found, these waves can actually now lead to a significant amount of transport. So if you're interested in the question of transport, drift is something that's quite important for you. Now, we have been talking about almost exclusively about a single wave. So we say, okay, this is my wave number kx, and I'm just going to focus about that particular wave number. Now, what happens if I actually have a wave packet? Obviously, this is a linear problem. So if it's a linear problem, the individual wave. So I can say that this can be written as a combination of bunch of waves. And I use this to create a wave packet. Right? So if these individual waves are obviously not interfering with each other, how do I understand the evolution of the wave packet? What should be my way of looking at this wave packet and trying to make some sense of it? So what's the right way of looking at the propagation of the wave packet? So if I just go back to defining this quantity, we had for all the waves, I can define something called as a phase at kx minus omega t. So all these problems, you saw that there was a function of y or a function of z multiplied by e to the power I kx minus omega t. So if I define a phase, which is kx minus omega t, I can say k is dou theta dou x, and omega is minus dou theta dou t. I can define the wave number as the spatial gradient of the phase, and I can define the frequency as the temporal rate of change of the phase. So even if I don't have a single wave, if I have a packet, then if the packet is identified in terms of the phase, so if I say that I am defining a wave packet, e to the power I theta of x comma t. So if I find what is the gradient of the spatial gradient of the phase, that tells me what is the local wave number. And similarly, I get an information regarding the frequency. So now if I use these two relations and write down what is dou square theta dou xt, a mixed derivative, that would be dou k dou t, or from the second equation, that would be minus dou omega dou x, which tells me that dou k dou t is equal to minus dou omega dou x. So I have obtained dou k dou t plus dou omega dou x is equal to 0. So here, because this is a wave packet, I'm basically defining a local wave number and a frequency. So then this is just an identity based on how I've defined k and omega. So I'm saying that for a wave packet, I'll define the wave number as the spatial gradient. So k is the spatial gradient of the phase, and omega is the negative of the rate of change of the phase with respect to time. So that automatically leads me to this equation. Now dou k dou t, I could also write it as so dou omega dou x, I can write it as the gradient of the frequency with respect to wave number multiplied by dou k dou x. If I have my dispersion relation where omega is some function of k, then I can write down an equation for the evolution of the wave front, which will be and this I can extend to three-dimensionality, where I can now say that this is the rate of change of the wave vector, the gradient of frequency with respect to the wave vector, dotted with the spatial gradient of, so this I should just write it as d omega dk, because omega is only a function of k, dotted with the gradient of k in space. So this quantity d omega dk, this actually tells you the propagation of the wave vector. So if you write down an evolution equation, a kinematic equation for the wave vector, then the kinematic equation for the wave vector is actually governed by this quantity d omega dk. In this case, if I write omega for the three-dimensional problem, this object is called as the group velocity. So the group velocity for a wave packet actually tells me how the wave vector propagates. And there is a way by which you can actually see this. For if you just consider two waves, let me just sketch this in the previous page. Yeah. So once again, for the interface, if I assume that the interface is a combination of two waves of different wave number and frequency. So I'm just assuming a simple example. And obviously, if you take a surface gravity wave, then omega is root gk. So now if I use a cosine summation, then I can write the sum of these two cosines as a product. So I can write this 2a cos delta kx minus delta omega t cos k bar x minus omega bar t, where your k bar is the average wave number, delta k is the difference, half of the difference, and similarly omega bar is the average frequency, and delta omega is half of the difference. So now you can say that for two waves, which are two traveling waves which are superimposed of different wave number and frequency, this can be represented as the evolution of a single wave. So I can now write this as some new a bar of x comma t multiplied by cos k bar x minus omega bar t. So I can then say that there is a carrier wave, which is the average of the two waves. And then there is an envelope, which is given by cos delta kx minus delta omega t. So if you were to look at how this would be, so I will try to sketch it. Let's see. So there would be a wave, a carrier wave that is propagating. This is the carrier wave, which is given by this. And there is an envelope which is given by delta kx minus delta omega t. So what is the speed with which the carrier wave propagates? The carrier wave is propagating with the speed omega bar by k bar. And what is the speed with which the envelope is propagating? That is delta omega by delta k. So in the limit of delta k going to 0, this becomes d omega dk. So you find that when you have a combination, when you have the wave packet, the packet is actually propagating with the group velocity. Whereas the individual wave crest and troughs, they are propagating with omega by k, which is called as the phase speed. So when you have this kind of an arrangement, the envelope or the wave packet actually propagates with the group velocity, whereas the individual guys, they are going to propagate with the phase speed. The phase speed is not really a vector. What is a vector is actually a phase velocity. That is the velocity pointing in the direction of the wave vector. The x component of this quantity is not the same as omega by kx. So, or Cpx is not the same as omega by kx. Cpy is not the same as omega by ky. So phase speed is not a vector. Phase velocity is a vector, which would be omega divided by the modulus of k, pointing the unit vector being along the. So if you draw the wave fronts, so if you have the wave fronts in your problem, so the vector which is pointed normal to the wave front, that is going to be the phase velocity. The group velocity carries information regarding the wave packet. And I'll write this without a proof. You can take the group surface gravity wave equation and derive this. That if you write down the energy, the kinetic plus the potential energy for the system, I mean, even in the linear regime, if you write this out, dou E dou T is carried by the group velocity. So if you write down the wave energy flux, so this quantity is the wave energy flux. The group velocity basically decides the propagation of energy. So Vishnu's question regarding the wave packet have more frequency. So is this omega a kind of average frequency? So are you asking about this particular omega, the definition for the group velocity? So yes, so this omega is a function of k. So you are not specifying what value of k is. So if you go back to now, let's see, I might have the picture here. So, okay, I'll write it first. So for surface gravity waves, omega goes as root gk. So let's write down the phase speed. So there is only one k here. So omega by kx is going to be root g by kx. Omega derivative with respect to kx will be half root g by kx. So in this problem, they differ by a factor of 1/2. Now, if you take the full equation, which was omega square is equal to gkx plus gamma kx cube by rho, if you take the full equation, this is how the phase and the phase velocity and the group velocity would actually look like. So your blue line is what is your group velocity. So given a wave number, if you fix a particular wave, so in a wave packet, the group velocity is actually deciding the speed with which, so I'm not sure if it was evident in the previous video. If you look at the top video, see the red dot and the green dot. So if you're identifying the direction of the propagation of the crest and the direction of the propagation of the wave packet, they're completely in opposite direction. So in some problem, CG and CP can be completely in the opposite sense. They're not even unequal in magnitude. They're also in the opposite sense. So if you give a value, so from the dispersion relation, you get an expression of omega as a function of k. Now you can say that this signal is actually, the top signal is actually constituted of a bunch of sine waves. Let's say you have 3 sine waves of different omega and different k, which superimpose and give you this. Each of those sine waves, they have a certain phase speed. I'm using the word phase speed and phase velocity interchangeably because this is just a one single degree of motion. If you have more than 1 degree of motion, then they are not the same. So if you just have a single degree of motion in the x direction, then I sum up 3 waves of different wave number and hence different frequencies. I can find out what is the speed of propagation for each of these entities. But when I sum them up and form the packet can move in a different fashion altogether. And the motion of the packet is actually governed by the group velocity. Does that clarify the difference? So here you have in the next case a plot of group velocity, phase velocity as a function of wave number, a rescaled wave number. Lambda is actually the wavelength, so this is a rescaled wave number. These are the pure capillary waves. The dashed lines are pure gravity waves, and the dashed dot lines are the pure capillary waves. And if you look at the blue curve and the red curve, they are corresponding to phase speed, and blue one is group velocity, and the red one, no, I'm saying it the other way around. So blue one would be the phase speed, and the group velocity would be given by the red one. So if you now look at it for the small k limit, so when you are somewhere here, then the problem is gravity dominated. So if you look at these two terms, the first term is going to dominate over the second term when kx is small, because kx cube goes to 0 faster than kx goes to 0. So you have gravity waves being dominated when kx is small, which means that you have long waves in the system. When you go to large kx, then this term is going to significantly exceed the first term. That's when kx is large, which means the wavelengths are significantly small. So that's when capillary waves are going to be more dominant over surface gravity waves. The continuous line is the combined problem. So you can see it nicely branches and goes from one branch, which is the pure gravity waves, to the other branch, which is the capillary wave. Now, the feature here, which we have been saying regarding this aspect of group velocity and phase velocity, the fact that they aren't equal, this is actually called dispersion. So capillary gravity waves are dispersive, which means that the speed of propagation depends on the wave number. CP or CG, either of the two, they're not independent of the wave number. So if you create a wave packet, let's say I create this wave packet, which, as I said, is a sum of several several sine waves and I turn it on at t equals 0, they're going to immediately separate out because they are going to move with different speed. So that's the fundamental feature of dispersion. So you will see this coming up in later lectures when theory is going to talk about solitons. So he will discuss that how dispersion and nonlinearity can compete with each other and give rise to a stationary or an invariant structure. So dispersion has the property or the behavior to separate things out. You were in a crowd, but all of you have different running speed. You don't run at the same speed. So in a marathon, automatically you will see a dispersion happening from the starting line because not everyone starts with the same speed. So automatically people who are running at a faster pace go ahead. Then there is somebody in the middle, and then there are people who are lagging behind. So that's the dispersion phenomena that you have based on maybe your training capacity, your body weight, your fitness, etc. You have different running speed. So waves in the same manner in terms of their wavelength have different running speeds or in terms of different phase speeds. So the moment you turn it on, initially you have a coherent structure which has been formed by summing up a lot of sine waves. Immediately they will start to disintegrate. Disintegrate in a sense that they are going to all move out. And because they're moving out at different speeds, you would actually not see that coherence that was there initially. And what nonlinearity does, nonlinearity tries to bring in a coherence. I mean, that's what he's going to talk about. So he will show that how the coherence building mechanism of nonlinearity and the decoherence effect of dispersion can compete and give you something which is like a nice invariant structure that does not change with time in terms of its shape. Now, this is all about linear surface gravity waves. You are going to look into a lot of aspects of nonlinear waves in subsequent lecture, but just to give you a feel, and since there was a question in the first lecture regarding an instability of an instability, or rather you find the perturbed state evolving into something else, and then you do an instability of that. So here, the surface gravity waves are stable. There isn't any instability for the surface gravity waves. Now you can ask the question that if I perturb the surface gravity waves, would that be unstable? So we are not going to work this algebra out, but what we have done is we have found out that in the linear theory, the interface deformation is some sine kx or cos kx minus omega t. Now, if you do this process in higher orders in amplitude, you can go all the way to a cos 2x and a cos 3 kx minus omega t term, and that's called as a Stokes wave. And you can see here for a given value of k naught a naught, how does the Stokes wave look in comparison to a perfect cosine wave? So the dashed line is the cosine wave. That's what we have been working with so far. You found the drift for that particular problem. We have been talking about the speed of propagation, dispersion, etc. Now, if you include the nonlinear effect, then that's the continuous line. And you can see it's not a perfect sine wave because it's a sum of 3 sinusoids, each of higher harmonics. So cos kx minus omega t, cos 2kx minus omega t, and cos 3kx minus omega t. So even at x equals 0, there's a slight increase, and then you can see the shape is not like a perfect sinusoid. The more interesting thing that you would observe is that here, if you calculate the frequency, we found in the infinite pool problem, the frequency for propagation of these waves would be root gk. Now here, there is an amplitude correction for the frequency. Depending on what is the amplitude of the wave, in the previous calculation, when we found the frequency was independent of the amplitude, as it should be for a linear problem. In a linear problem, the time period of oscillation or the frequency of oscillation should not depend on the amplitude. That's the premise of a linear calculation. Any linear vibration problem, the amplitude is not something that enters into the final results that we obtain. So it's valid for arbitrary amplitude as long as it is infinitesimal compared to something else. But the moment you go to the nonlinear correction, then the amplitude enters into your calculation. You need to specify what the amplitude is. And that's what you see here, that the frequency now becomes amplitude dependent. So there is, besides a dependence on wave number, there is a dependence on amplitude. And this, if you remember again from the first lecture, we worked out the frequency for a simple pendulum, root G by L, that I have a single degree of freedom, the frequency is root G by L. And there, if you were careful, you would have noticed that I made the small angle approximation. I said that in the governing equation for the pendulum, sine theta is approximated as theta. If you don't do that, you can still go ahead and solve the problem. In that case, it turns out it's soluble. And if you calculate what omega is, omega then in the next correction will have a amplitude correction, pretty much a quadratic correction in the amplitude. You would find in that problem also. So this amplitude correction is something that's prevalent in most oscillator problems. When you do the nonlinear effect in the calculation, the time period becomes dependent on the amplitude of your oscillation. Now here, just like you had a dispersion in wave number, you have now a dispersion in amplitude. What does that mean? If I choose an exact same wave number or a wavelength, but of different amplitudes, their speed of propagation would be different. The speed at which they move now also depends on the amplitude. So you can have identical wavelengths, but of different amplitude, and they're going to separate out. So this is a purely nonlinear effect. This is not then the linear theory. In the linear theory, the dispersion is because of differences in wavelength. But now what I'm saying is they can have the same wavelength and they can disperse out or they can separate out if they have different amplitude. And that's a nonlinear effect. Now it turns out this Stokes wave, which is a nonlinear solution of your governing equation, at least at this order, is unstable. So if you do a stability analysis of this base state, you assume this is your base state and you do a stability analysis, it turns out it is unstable. So this is a set of experiments that people used to do quite early, where they had a paddle in a pool, in a tank, and used to oscillate the paddle to create these rows of waves. And obviously the paddle used to oscillate large enough amplitude to create these Stokes waves. Now they used to always observe, so this A that you see on the top is which is pretty close to the paddle location, and the B snapshot, the picture, is what you observe when it's significantly downstream from the paddle. And they used to always observe that these wave trains that were there, when it has traveled some distance downstream, it used to disintegrate. And for a while, they used to think that this is due to some imperfection in the paddle, that you probably have not done it well enough. Okay, there was a question. Sorry. Devjit is asking, what is the operator O? So the operator O is just telling me what terms I'm ignoring. So that's called the order in the order of terms that I'm ignoring. So the terms that I've not written out there, those are terms which are order at least a cube in amplitude, order k naught a naught cube. So there will be terms k naught a naught cube, k naught a naught to the power 4. I'm not writing them down. I'm just taking the term up until order k naught a naught square. Okay, so this set of experiments, when they used to do, they found that, so first they thought this is probably due to some imperfection in the paddle, that they were not being done carefully enough. Something needs to be done to improve the quality of experiments, but it's continuously kept happening. And it was only when Brooke Benjamin looked into this problem. So these are experimental snapshots from Benjamin and Hasselmann, and this instability was done by Brooke Benjamin and Fair, where they found that these Stokes wave trains are actually unstable. And the instability of these Stokes wave trains manifest in terms of these waves breaking. And you can also see this because now, since we have access to reasonably good simulation, so this is a Stokes wave. So the interface has been initialized with a Stokes wave. And you can see that as you have initialized it, it breaks apart and forms these So you can clearly see how the wave front that is there, the Stokes wave front, that actually breaks apart. So this is an instability of a stable wave, which was your base state. So when you did the base state calculation, you found out a wave, you found out this frequency of propagation, you were happy at the linear order, you went to the non-linear order and you still found out a wave which was all nice and perfectly resolved in terms of the frequency and etc. But it turns out that this wave is unstable. This wave cannot actually sustain itself and it will break. And this is what is called as the Benjamin fire instability. The last part, this is our dispersion relation as a function of all the parameters. So we go back to where we started from. We had a top layer which is moving with a velocity u, two liquids having different density, and there is surface tension. Now you can ask the question that given this expression, what is the minimum speed with which the top layer should move such that it becomes unstable? So you can take that, you can take this expression, it's a quadratic equation in omega. You can solve this quadratic equation and you would find that there would be a term inside the square root which needs to change sign for it to be unstable, because we are in search of omega being an imaginary quantity, or at least omega having a non-zero imaginary part. So if omega needs to have a non-zero imaginary part, then there should be some criteria regarding the problem to be unstable. And that would be a criteria involving all the parameters and u and kx. So for a given kx, there should be a u that is required for it to be unstable. Why is that? Because if your k is extremely small, you have very long wave disturbances, you would find there is a restoring mechanism. See, if you don't have any density jump, you get back the Kelvin-Helmholtz instability. We saw that earlier. If ρ1 is equal to ρ2 and gamma is equal to 0, then you would have the Kelvin-Helmholtz instability where it would just grow unboundedly. Now, if you make k very small, the wavelength is extremely large, then the gravitational restoring mechanism can prevent the instability from occurring. We are again thinking of air-water system. Nothing funny about that. We are taking the air movement into the picture. We are letting the water layer be of water density, but of quiescent condition. So if the gravitational restoring force, that when you perturb the interface, which gives rise to the surface gravity waves, when there was no flow, when you perturb the interface, there is a restoring mechanism due to gravity which leads to these waves propagating. So now this restoring mechanism of gravity can actually prevent the instability from occurring if the wave number is too small. Similarly, if the wave number is too large, then you cannot have an instability because surface tension is going to be the guy which will champion over everyone. It's such a strong mechanism that the moment you create a hump, it will try to stretch the hump and make it flat. So both gravity and surface tension will try to remove any undulations and make it into a flat interface. So the instability only will occur in a band of wave numbers, larger than some value, smaller than some value, when both gravity and surface tension are operational. And if you then ask the question that at what wave number would I get the minimum speed, like any speed lower than this, I would not find any instability. This would be the expression. It would involve the density of the two fluid, the surface tension term, and that's the minimum speed. So this is how the real part of omega and the imaginary part of omega would look. So if you were looking at the imaginary part of omega, you want that to be non-zero. So if the velocity is 1.2 times that u critical or 1.5 times u critical, you actually get an instability. So the green line is corresponding to u being 1.5 times uc. The black line is when it is 1.2 times uc. But the moment u is equal to 0.8 uc, there isn't any instability, as it should, because if the top layer is moving with a speed lower than this critical speed, there would be no instability. Now, how about using this to argue for waves being generated due to wind in the ocean? So when there is wind blowing over the ocean, if you assume that the wind blowing over the ocean can be mimicked using this setup, what is the minimum wind speed that is needed in order for the generation of waves? We can ask this question using this toy problem, right? We have worked out what is the minimum wave speed, minimum wind speed that would give rise to an instability. So if I say that these waves are nothing but an instability that is generated by a layer of wind that is blowing over the water surface, I know all the values. Rho1 is approximately 1, Rho2 is approximately 1000, G is approximately 10, and gamma is 17 to the power minus 3. So can someone just substitute these values and tell me what is an approximate value for UC for an air-water system? Assume Rho1 to be 1, Rho2 to be 1000, and gamma to be 17 to the power minus 3. What do you get for UC? Any answer for it? Around 7 meters per second. That sounds right. Yes. So a bunch of you are getting around 7.37 meters per second. So that tells you that you need the wind to actually blow with approximately 7 meters per second in order for the waves or this instability to set in. Now, this is in contradiction to the observation. Observation shows that these observations are both done in the lab as well as observed in situ in the open ocean or lakes, that if you have much lower winds which are blowing over water surfaces, you can actually have an instability giving rise to these waves. So what's the part that is being missed out? So here, what we have assumed is that this is like a Kelvin-Helmholtz instability. There is a plug flow that is blowing over the water surface, and it's the speed of this plug which decides when the instability would occur, and we found it to be approximately 7 meters per second. Now, the actual wind blowing over the water surface would be first a turbulent, but more importantly, there would be a boundary layer. So that velocity u with which it is actually moving, that velocity u would not really be immediately on the surface of the wind, surface of the water, but there would be a certain height over which the velocity would vary and approach that velocity u. So to argue for this discrepancy, Miles came up with a theory, and this is where you make, there were again questions earlier regarding doing the inviscid stability for a viscous problem. Now here, this is an inviscid stability of a turbulent base profile. So Miles had this quasi-laminar theory. He said that the wind flowing over the water surface is a turbulent wind. And if you assume a turbulent boundary layer, you take the mean velocity profile, and then you do a stability analysis of that velocity profile. So it's a quasi-laminar theory. The velocity profile that you are using in your inviscid analysis is a velocity profile that is obtained from a background flow that is inherently turbulent in nature. So the velocity would actually vary in space, and finally it would attain the uniform stream far away from the free surface. So if you do this, What Miles found is that as this shear flow, so this is no longer a plugged flow, as this shear flow tries to flow over the free surface, this is not a rigid flat plate. We study flat plate boundary layer. This is not a rigid flat plate. This is a free surface. So as it tries to flow over the free surface, and there is quiescent water below, it's going to actually create deformations of the free surface. And we learned what happens when there are deformations of free surface. There are gravity waves. So when these gravity waves get created because of the shear flow moving over the free surface, these gravity waves can move with a wind speed. So let me write down hypothetically. The CG equals U, the background flow U, at some height ZC. So you have this shear flow over the water surface. It's going to perturb the water surface. There would be waves on this water surface, gravity waves. So this perturbation on the free surface can move as fast as the shear flow at some height. Let's say this is ZC. If that happens, the perturbation can extract energy. So this location is called the critical layer. So when you look at the Rayleigh equation has this mathematical funkiness where this term can actually go to zero at some location in the domain. If C is equal to U somewhere in the domain, then the pre-multiplier to the differential equation vanishes, or the highest derivative vanishes. So that's a singular differential equation. So when you have this kind of a critical layer happening, the perturbations can basically amplify by interacting with the flow at that critical layer. And this leads to an instability. So this is called the Miles mechanism of wind-generated waves. So you can take an actual turbulent boundary layer profile like a log layer and do the calculation, which is what Miles had done. But there are some velocity profiles which are not necessarily exactly matching with the log layer profile, but still nonetheless captures some features. And if you take an exponential profile, so a velocity profile which starts from zero and approaches the uniform flow in an exponential manner, the advantage is that you can solve this entirely analytically. You don't need to do any numerics in this problem. What you find here, if you recall the previous graph, that at 0.8 UC, so if UC was based on that 7 meter per second that all of you found, at 0.8 UC also there is an instability. And it turns out if you plot the growth rate contours in the U versus K plane, this is what you had before. At around, it's actually around 6.5. If you put realistic values of rho and rho 2, I mean, not just put 1 and 1000, if you take it to be what is for seawater, then you get it to be around 6.56 meter per second. This is what, so this, I have swapped the figure. This corresponds to the plug and this corresponds to the shear flow. When you consider the shear flow, it turns out this is much smaller. You can get an instability even at 2.5 meter per second. Now, how do you know all of this is all fairy tale and not making any sense? I mean, how do you verify all of this? Is there some proof for any of these things? So there's some. It's not, I mean, as you would expect for an uncontrolled ocean, you can't really get data as easily as you would get for a controlled lab experiment. But what you have here is a classical plot from a paper by Plant in 1982, where you have the wind speed scaled by the speed of the instability and the growth rate scaled by the frequency, plotted based on miles. So this is the miles growth rate, and the scatter that you see all over, that's what you get from different set of experiments. So this is, we have started from a very simple scenario of a uniform flow flowing over a quiescent medium with a free surface, with an interface of two different density. We use the kinematic and the dynamic boundary condition. We are able to then come to the derivation for the dispersion relation. We saw two circumstances, one where there was no flow, where you have surface gravity waves coupled with capillary effects, and then there was the other one where there was Kelvin-Helmholtz instability when there was no density jump. Then we found out that the capillary gravity waves, if you take that velocity profile, that allows for a non-trivial transport. You have this feature of Stokes drift, where particles in a geophysical setting, because of the vertical variation of the velocity, it can, after every time period of the wave propagation, it can undergo a transport. We also saw the feature that these are dispersive waves, which means that the wave speed depends on the wave number. And more importantly, there are two ways of understanding the wave propagation. One is the speed with which the wave front propagates, which is the phase velocity. And the other one is the speed with which the wave vector or the energy propagates, or the wave packet propagates. That's the group velocity. And they're completely different, and they won't necessarily coincide either in magnitude or direction in a given problem. We saw for capillary gravity waves are obviously dispersive, and depending on the wave number regime you're operating at, you would see either gravity dominated physics or you would see capillary dominated physics. Then when we came back to the problem of gravity waves, we said, what happens if I have nonlinearity? So without any derivation, I just told you that there is a way to extend this to higher amplitude, and you get an expression which is called the Stokes wave. So that's an expansion in amplitude. But the interesting aspect is, here there is an instability of this nonlinear wave that we are talking about. So you take the starting problem is a quiescent static state, no flow, air, water. You forget even air in the problem. You just say that it's water with a free surface. So it's a stress-free boundary condition. You solve for the linear problem, you get surface gravity waves. You go and do the nonlinear calculation, you get a modification to the surface gravity waves called the Stokes wave. And then this Stokes wave turns out to be unstable. And again, all the while trying to show you that these things are observable. So what you would observe in these terms of these wave trains breaking and the wave trains actually becoming unstable is a manifestation of the sequence of building of waves and finally finding that one particular nonlinear wave becoming unstable. And the last thing that we went through was go back to the problem where there is a flow on top, and then ask the question that is there a way by which these winds blowing over the water surface can generate waves. So the calculation that we set up, that tells us that there is a minimum wind speed, which is approximately 6.5 meter per second, that's needed for the instability to set in or these waves to form, which is significantly higher than what you would observe in experiments or field observations. And then we went back, or rather we got introduced briefly to what Miles hypothesized, that let's make this kind of an ansatz where we assume the turbulent shear flow over the water surface and do an inviscid stability analysis of that flow profile. When we do that, we are able to recover an instability at much lower wind speeds. There's still a scope of a lot of things that are being done and can be done in the field, but that should at least give you an overview that you can take this simplistic setting and observe some quite fascinating aspects. So just to end, big thanks to Ramana, Nishant, and Yashodan who helped me put up a large part of these slides. They did a bunch of many of these calculations. And we end today's 2 lectures. Thank you for all being around. We start tomorrow at the same time at 1:30, where Mani would be talking about linear internal waves. So all the while I have been saying that the fluid are of constant density. The fluid has no variation in density. The only variation was at the interface. So he'll basically take the circumstance where there is a fluid which has a density variation spatially. It's not a jump. and what kind of waves you would get, work out the dispersion relations for such a setting. And then in the evening, you would have Silva talking about experimental methods. So with that, thank you everyone, and I'll be happy to take more questions now.
Hello.
Yes.
So yeah, in the case of the turbulent profile in the about the waves, like are we considering that the profile is like from the based on a solid wall, or based on like a water interface, air-water interface?
So yeah, you should ideally, to do it in an exact manner, take the velocity profile for a turbulent boundary layer over a free surface. But the origin of the instability doesn't really care about the exact profile. Obviously, the growth rates that you're going to compute would have some differences based on the exactness of the profile. But the fact that there is an instability, which is different from the Kelvin-Helmholtz instability, requires a shear profile, which means it requires a curvature in the flow profile. It cannot be like a linear profile. It needs to be a profile that has some second derivative. That's what
So
Miles said. So, go ahead.
If we had used an Blaze's profile also, would we have gotten this?
You would have, you would have obtained it nonetheless in that case also. The growth rates would differ. So what you need is, what is that is required? The thing that is required is that the gravity waves which are propagating, or rather which would have propagated on the interface if there was no flow, their speed needs to match or will match with the shear flow at some height. At that location, the vorticity gradient should be non-zero. The vorticity gradient is the second derivative of the velocity, proportional to the second derivative of the shear flow. So you see, it's a very general criteria for the instability to be there. Now, what growth rates you find, that will depend on the exact flow profile you take.
Okay.
But so Miles had done it for a log profile. Others have done it for an error function. The exponential is what I showed because that's something which can be done entirely analytically. It's a little complicated in terms of the solutions you get analytically, but you can still do it without solving a differential equation. Because what happens when you try to solve that differential equation, there is a singularity which would be there if there was no instability. So if you... So this term, if C was purely real, then this term would go to zero at the location where I'm saying is critical layer, where
which
C
term,
is
sir? Okay, all right. Yeah.
Okay, so what I'm saying is, if C equal to U at some height, then this equation would be singular.
Okay.
Now, if C has an imaginary part, then the real part can equal to U at some height, but the imaginary part, since it is non-zero, then this term would be not vanishing.
Yeah.
So when you do the numerical calculation, you have to do it carefully, because sometimes the code actually can do funny things if it is not able to capture the imaginary part. And if it is only probing the real part, then besides not finding the imaginary part, it is also going to find the equation to be singular.
Okay.
So you have to do that integration carefully. So usually the way it is done is that when you are solving it like a traditional boundary value problem, you try to come from both sides of ZC and then try to match it at ZC. So it becomes slightly subtle from a numerical point of view. So if you take the exponential velocity profile, that has an analytical solution. So you can quickly get these results and see that there is a instability at a lower wind speed without immediately going to a numerical calculation. But obviously, if you need to match it with the field data, you need to take more realistic velocity profiles.
Okay. One other doubt is that, so what if we considered that there was a current inside the water? Would that would make a difference?
Oh yeah, huge. That's a very good question. So I didn't want to show it because Yashodhan has done some of these. I don't have the plots here. So it makes some difference. So there is one more instability which comes in. That's a good question. So what happens is, if there is a current, so there is something called the wind drift layer. So if you, I might draw it quite bad. So if you have another flow inside the water layer, the wind drift layer, then you have the Miles instability, and then you have at very large K, you have another instability. So very small scale instability called the ripple instability. So people have also observed sometimes that second kind of instability. So they occur together. If you are aware of the fact that the water layer is not really quiescent, the water layer also has a current in it.
Okay.
And
So,
yeah, and I'm just to finish the point. I mean, we are not talking about these things being done 50-60 years back. These are results which people have arrived only 2 or 3 years back.
oh,
I mean,
okay.
I'm talking about the wind drift question that you had. That
Okay.
calculation is only 3 years old.
Oh, okay. Okay. So, could you tell me the paper, like, where I can refer to this?
Yashodhan, what is the year?
I think it is 2014.
Okay, so I was off by another 3 years. Wolf and Young, JFM 2014.
Thank you, sir.
Yeah. Okay, so Suraj has a question. What could it mean for a wave vector of the wave packet to be a function of time? So you are not dealing with an individual wave here. You're dealing with a packet. So when you are dealing with the packet itself at some location, you can define a local wave vector, and that would be due to the cumulative effect of all the waves that are forming that. So that could definitely be a function of space and time. So this is obviously a concept that you are defining for the wave packet, not for the individual wave, because a wave packet by definition does not come with a constant wave vector or a constant frequency. Does it make sense, Suraj? So all that definition that we are talking about, writing the group velocity and all, these are all for a packet. If you are thinking from the point of view of a single wave, then for a single wave comes with a unique value of k and then a corresponding frequency, numerical values. Apart from the critical wind speed being different, does the wavelength of the instability also change when using the Miles hypothesis? So the wavelength, I think, remains largely, well, I think it gets pushed a little lower. So here it's roughly 1 meter. And in the other case, you get it at significantly smaller. So this wave number, so this is the case when it is a plug. This wave number is where the gravity waves and the capillary waves are moving equally fast. It's somewhere here. So when you do the Miles thing, it occurs at few meters. Any other question? Vishnu had a question. Did I answer Vishnu's question? Can we get an idea if the instability is absolute or convective? Yes, I didn't show how it is done. It's again based on, I mean, it's not a one-word answer how to do it. The picture that I showed is probably the one-word answer, trying to see how the wave packets move. But how to identify it would require you to take the dispersion relation, analyze it in complex omega, complex k plane. So I don't think I'll do justice, give a one-word answer, but it's looking at the dispersion relation in the omega k plane. You try to analyze. Well, I think because it requires you to find out what are called as saddle points in the omega k plane. Maybe I'll just so what I'll do is I'll anyway try to share some references which all of you can go through, because trying to say it in a word I might confuse you even further. The simple picture is obviously trying to look at how the wave packet grows, but identifying it is more non-trivial numerically. Like given a problem for which you're doing a linear stability calculation, doing that kind of a diagnostics is significantly non-trivial. So maybe I'll just direct you to that reference, and once you have had a look, you want to know more, feel free to drop a mail or talk to me on email. I mean, it's more detailed analysis of the dispersion relation. So you can't just say that I look at the dispersion relation and I'm able to figure out how would this problem be absolute or convective. It would depend on looking at the branches along which the gradients of D or the dispersion relation. So you would take the dispersion relation and work with that. Any other question?
Sir, this is based on something I've read, and not related to the talk as such. But suppose we have a flow in which you have you don't have an invariance in the in two directions, and we take a form like f of the amplitude is f of x comma y and x comma t. Let's say it's not invariant in time and not invariant in the x direction, but it's invariant in the y direction, let's say, and you take it as f of x comma t and e raised to I omega k y, and you get, and in the end you get a wave equation of f of f. Then can we then use like e raised to I kx kx minus omega t, and then solve that wave equation?
No, so is your background varying in time and x?
Yes.
So if your background is varying in x and t, then you can't obviously assume a form of e to the power I kxx minus omega t in the problem. Unless you make an argument like boundary layer where the flow is varying much slowly in the x direction, or for unsteady problems, if you say that the flow is like it's like a diffusing problem. So if you have a vortex which is diffusing, so the diffusion of the vortex is happening significantly slowly, and you are trying to probe the instability. So you can either assume the flow to remain frozen, that's like a perfect steady problem, or you can be a little more, you can be a little better than this and say that, okay, the flow is evolving, but the evolution of the base state is happening on a time scale that's much larger than the instability time scale. So you do an analysis just like the way we wrote it for the boundary layer, where you assume a variation on a slower time scale, which is the variation on the time scale of the vortex. And then there is another time scale, which is the variation on which the instability sets in.
Okay, sir.
So
that's the only way.
Yeah. So I didn't probably say that when I was mentioning that there's also a mathematical reason why it becomes more complicated to assume a Fourier mode in x if the flow varies in x, or a Fourier mode in time if the flow varies in time. Imagine you have a differential equation, and these kinds of normal modes are effectively doing a Fourier transform in time or space, or a Laplace transform in time and a Fourier transform in space. Now, what happens is that if the background varies in a particular direction, let's say the background varies along the x direction. So in such a circumstance, since the background varies along the x direction, if you are trying to do a Fourier transform, let me see if I can pull this. So if you look at this equation, if you look at the top equation and if you assume that it is varying in the x direction, so what does it do? The second term and the third term, you are solving for the small u, but they are multiplied by coefficients which are functions of x.
Yes.
Right?
Yeah.
Now, if you try to take a Fourier transform in x, these terms are okay, but these two terms will give you a convolution.
Okay.
So the u is an unknown and grad u is some function of x. So when you try to do a Fourier transform, you can't write it explicitly as the transform variable u hat or something like that. So mathematically, it will lead to a convolution. So that's the so we discussed the physical reason why it doesn't really make a lot of sense if there is a strong variation in x to seek for a wave-like variation in the x direction. Okay. But mathematically also, you will land in trouble that you will not get. I mean, one reason for assuming it to this particular form is you reduce the degrees of freedom, or you reduce the order of the differential equation from a PDE to an ODE.
Yeah.
You reduce a lot of these differential operators to algebraic operators. Now that won't happen. You would still end up having some kind of convolution terms.
Okay. And
okay.
these convolution terms are difficult to solve, is it?
Yeah, I mean it defeats the purpose why you tried doing this. So physically, it becomes difficult to make sense of what is a wave in a direction in which the flow is varying.
Okay. Okay. All right.
So for instance, like if you have a material which is which has very strong temperature gradient, and you are looking at the propagation of sound waves, then you would not necessarily say that the sound waves would have a nice plane wave form in the direction of temperature gradient. Right? It will be more non-trivial. The structure of the propagation or the structure of the wave along the direction in which the temperature is varying, because that would change the speed at which it propagates, or some material heterogeneity. Let's say that it is not propagating through a homogeneous material, but the material is highly heterogeneous. So in such a circumstance, you can't identify a single wave moving through the medium, because as the wave moves through the medium, it is encountering different regions of heterogeneity.
Yes.
So it physically becomes tricky, and it mathematically also is tricky, because your purpose was, otherwise you could have taken this linear PDE and just solved it numerically, right? That you can do any day.
Yeah.
It's just that solution that you are obtaining is specific to a given initial condition. So just to avoid having initial condition specific solutions, you are doing this exercise of normal modes.
Okay, sir. All right.
Yeah. Okay, Shiva Prasad has a question: how to do a temporal analysis experimentally to verify these results? So temporal analysis, if you want to do it, you can create some kind of an undulation. Like usually, if you want to introduce or excite the system at a particular wave number, you can either create some kind of a surface undulation to trip or trigger that particular wave number, which would then give rise to an instability in time. So it could be in terms of that surface, or you can, I mean, that's typically what I know how you can do it. Now, for certain systems, you don't need to be that careful. Like if there is an temporal, like for instance, Kelvin-Helmholtz, when you saw Kelvin-Helmholtz instability, you don't really need to do much in order to excite that instability. You can pretty much see the growth rate, and if you want, you can calculate that growth rate from what you observe in experiments and match it with your theory. Taylor-Kuwait, not much needs to be done to excite the temporal instability. The inherent noise in the system is sufficient. But for some problems, you might actually have to trigger it by creating some kind of a wavy boundary condition or wavy excitations in space. But Rayleigh-Bénard, Taylor-Kuwait, Kelvin-Helmholtz, these do not require a lot of, babysitting. They will mostly just trigger an instability with the inherent noise in the system. Any other question? Okay. If there aren't any other question, we will then meet tomorrow with Mani's talk at 1:30. Once again, thank you for joining, and we'll share the video links. Anyway, they are going to be on YouTube, but we'll also share the video links, and for the future talks, the material. So what I'll also do is I'll make PDF of these presentations and put them on the drive, so you can go through them later if you feel the need. Thank you. Ramana, could you stop the recording?
Stopped.
Thank you. Ramana, did you manage to stream finally?
Yes, sir. It started 5 minutes into the talk.
But so it didn't have the initial 5 minutes, is it?
Yes, sir.
Okay. Is the streaming paused?
Yes, sir.
Okay.